So we start with a textbook definition of the basic trigonometric functions. We've got a unit length, which is the radius of a circle, and the projections of that radius onto the horizontal and the vertical axis are the cos and sine functions. Now this same triangle can be represented differently using a proposition proved in one of Euclid's books. This is a proposition 31 where a semicircle with two secant lines each line originating from one end of the diameter meet at a point on the circumference. That angle, they meet at a right angle. Therefore, a right angle triangle is inscribed in the semicircle, and if we assign the diameter a unit length, then the sides of the inscribed triangle are the cos and sine of that particular angle. And something I'll be using later on is the fact that I can mirror the semicircle and the properties are all the same. Now, I'm going to now combine these two drawings, the small circle whose diameter is the unit radius and the larger circle whose radius is the unit length. And I'm going to take the cos side of the inscribed triangle in the small circle, project it so it intersects the large circle, and then drop down a perpendicular to the horizontal line, and I've defined, we can see cos of the angle alpha, which is the same length as the side of the inscribed triangle, cos alpha. And similar with the opposite side of the angle alpha in the inscribed triangle, given the right angle and the unit length of the diameter, we have sine alpha. And if we make the same extension of the line and making a projecting that intersection point down to the horizontal, we end up with another representation of sine alpha using the larger circle. So in summary, we've really developed the sine cosine functions using two separate images. We've got the smaller circle with the diameter as unit length and the larger circle with the radius as unit length. And at this point I hope you can recognize that both these triangles are identical and that the one on the left hand side is simply oriented at a different angle than the one on the right hand side. Let's just take a look at a quick 30-second version of this animation just to get an idea of what's happening beginning to end. So there it is. Now, the animation starts off with the standard rotating vector where the horizontal and vertical projections represent cos and sine. But to this I've added this blue circle which rotates along with the rotating vector, which is the circle of Euclid's Book III, proposition 31. Now, let's make this circle and the rotating vector the stationary reference frame. And with this as the stationary reference frame, we have an animation of proposition 31 found in Euclid's Book III. The point that is moving around the blue circle is the same point that was moving horizontally along the x-axis in the first part of the animation. And the moving sides of the inscribed triangle are the cosine projections. Now I have shown the large circle rotating, but I'm only doing this as a visual aid for those who might have difficulty relating back to the first part of the video. So also note how the point makes 2 complete rotations around the blue circle, whereas in the first part of the animation, the unit vector made a single revolution. This geometric relationship, which can be expressed in many other ways, is the foundational principle behind all the half-angle identities, and as well as the law of tangents.